Okay, the topic today is secant and tangent lines, which is really the beginning of differential calculus, the heart of differential calculus. So, some definitions. A secant line is a line that joins 2 points on a curve. Very simple. Just take any 2 points on a curve, join them, and the blue line is a secant line. Now, what we're going to want to do with the secant line is calculate its slope. And the slope of the secant line gives us something very important, and that's the average rate of change of the graph. You've talked about the concept of rate of change with lines. So, for example, if this was a position time graph, meters versus seconds, then the slope of the line would give us the number of meters rise over the number of seconds. So the slope of a secant line is the average rate of change on the given graph between the 2 points P and Q. So now what I'd like to do is to move towards talking about a tangent line. And you might have experienced the word tangent in the past, and I'm not talking about the trigonometry tangent. I'm talking about a line that touches a circle in 1 point. So the line shown here is tangent to the circle. It touches the circle just in that 1 point. The definition of a tangent being a line that touches a circle in 1 point, though, is a little bit more problematic when we start dealing with curves. Because if you have a curve, and I say, let's draw a tangent at that point, if we go with the idea that it touches the curve in 1 point, some people might think that the line looks like that, when in fact the tangent would look more like that. It would just graze the edge of that 1 point. So we need a more specific definition. So to come up with a more precise definition of a tangent line, I'm going to refer to this demonstration from the Wolfram Alpha site, and you can interact with this yourself. But I've got a curve here. The equation of the curve isn't important. I have a curve and I've got a secant line. And I've got a couple sliders here. The H represents the distance between the 2 points horizontally. So from this here to this here, this distance here would be H. So I can change my secant line. And you'll notice on the bottom that I've got the slope. I can also move the 1 point specifically to where I want it. Alright, now the tangent line, I'm just going to flip it on. The tangent line for this curve, if I talk about the tangent at this point, is right there. Now the question is, why is that the tangent line versus, let's say, a line that goes like so? Alright, so the whole idea is that as these 2 points, which in my previous diagram I called P and Q, as I move this point closer and closer to this other point, I'm going to shrink the H unit down. Notice that the secant line is getting closer and closer to the blue line. And that's really what a tangent line is. It's the line the secant line becomes as the 1 point approaches the other, as the horizontal distance H approaches 0. Okay, so the secant line is slowly, and you can see the slopes at the bottom. The slope of the secant line is approaching the slope of the tangent line. So the blue line's a tangent line because the slope of the secant approaches the slope of that blue line. Alright, so back on our main diagram, here's our definition of a tangent line. A tangent line at point P is the line L if the slope of secant PQ approaches line L as Q approaches P. So as Q gets closer and closer to P, I have a new secant line, Q's moving closer, I have a new secant line, and as Q gets really close to P, I eventually get this line, L, which is the tangent line. And remember that we were defining our distance H as the horizontal distance between P and Q. And I can symbolically say my definition of a tangent from above by saying that the slope of the tangent L is equal to the slope of the secant if Q approaches P, which is a limit. So the limit as q approaches p, or another way to say that, horizontal distance h approaches 0. And whereas the slope of the secant line was the average rate of change, the slope of the tangent line is the instantaneous rate of change, the rate at that one moment in time. Alright, let me demonstrate these two concepts using this particular function. I have a graph of the function here, and the first thing we want to do is find the slope of the secant, joining where x is -2 and x is 1. So my secant line would look something like that, and the slope of the secant is the difference in the y-coordinates over the difference in the x-coordinates. So I need to know what f of -2 is, so I could plug -2 into my function. We get 4 minus 6, -2 plus 1 is -1, and f of 1 would be 5. Substituting those into my formula, I get a secant slope of 2, which means an average rate of change over this interval between -2 and 1, an average rate of change of 2, which means my graph is changing 2 units of y for every 1 unit of x. It's a 6:3 ratio, which reduces to 2:1 average rate of change. So next we want to find the slope of the tangent line at x equals -2. It looks something like that. So what I'm going to do is I'm going to take my function, and my point's approximately here, and the coordinates of that point we know are -2, f of -2. And we know that the slope of a tangent is related to the slope of the secant. So what we always have to do is take a point close by to this, and just so you can see it, I'm just going to put the point here. This was an x-coordinate of -2, and here, remember we talked about the value h, which was the horizontal distance between the two. That would make the coordinates of this second point -2 plus h, comma, f of -2 plus h. And there's my secant, okay? Whereas here's my tangent. And the point is we want to make this point, which we called q previously, approach p. We want h to shrink down to nothing so that we get the slope of the red line, which is the tangent line. Alright, so to do the slope of a tangent, we do the slope of a secant. And then we take the limit as h approaches 0. In other words, doing the slope of the tangent involves doing a particular limit. So let's calculate the slope of the secant line. That's going to be f of -2 plus h minus f of -2 all over -2 plus h minus -2, which is h. Okay, let me just write our function here so we can see it again. Remember that it was x squared plus 3x plus 1. So I need to evaluate this limit. So the slope of the tangent is the limit as h approaches 0 of f of -2 plus h, which means plug -2 plus h wherever I see x, minus f of -2, which previously we calculated to be -1, all divided by h. So now we need to evaluate this limit. Multiplying out on top, and I've got 4 minus 6 is -2 plus 2 is 0. All the constants are canceling out. So I'm down to h squared minus h over h. I can factor out an h up top. Those cancel. And so my slope of my tangent is the limit h approaching 0 of h minus 1. Now, just before we finish this off in evaluating it, remember the h minus 1 is my slope of my secant. And if I just think about what's happening here, as h gets closer and closer to 0, I'm approaching my tangent slope. So let's suppose that the horizontal distance between the 2 points was 3 units. That would have meant that the slope of the secant, in which the points were 2 units apart, would have been, plug it in, 3 minus 1, 2. And if you think back to the first example we did, I'm just going to roll up to it. When I did my secant slope, in fact, my two x values were 3 units apart. And the secant slope at that moment was 2, just as my formula is showing. But now as this distance shrinks down, h approaches closer and closer to 0. So if the 2 points were just 1 unit apart, the slope of the line would be 0. If the 2 points were just 0.5 units apart horizontally, the slope would be negative 0.5. If the 2 points were just 0.1 unit apart horizontally, the slope would have been negative 0.9. So if they were not at all apart, if they were infinitely close, h approaching 0, my slope would be negative 1, okay, which is the slope of the tangent line. To evaluate that with algebraically, I just need to make h approach 0, and there we go. So just one final question that often goes along with calculating slopes of tangent lines, and that's to calculate the actual equation of our tangent line. We know that the slope of our tangent is negative 1. We just calculated that on the previous screen. And we know to do the equation of a line, there's lots of ways to do the equation of a line. One method I could use would be the point slope form. There's the equation of a line. I know that I need the slope, and I need to have one point. And of course the point I want to use is the point of tangency. So I'd need to know the coordinates of this point, which we've calculated before, negative 2, negative 1. So that can be popped into the formula as y plus 1 equals negative 1 x plus 2. And there's my equation of the tangent line.